Cool, so welcome again tonight. So tonight's a tech talk. So when I think of tech talks, I think of this gentleman. I believe you guys, don't worry, it's not one of those talks. I'm not that entertaining. But some of you guys might be a fan of...
He's not that entertaining either.
I thought it was funny.
Okay.
You might be a fan of Richard Stallman if you use GNU or GPL, or maybe you're not because of his rather extreme views. But I'm a fan of him for a different reason. I really like his wardrobe. And I'd love to know where I can buy that shirt. Does anyone know where to get that shirt? Okay, cool. Amazon. I checked Amazon. It was all. So I know this problem doesn't matter as much to engineers because if you're like me, you just buy the same thing off Amazon until it's sold out. But then you actually have the same problem because you want that same shirt. And Nate's wearing the same shirt as myself today. You want that same thing, but you don't know where to get it. And doing this computationally from the picture is a problem known as visual search. And visual search is one of the applications that LOPQ, the paper we're going to talk about today, is used for. So today, I'm going to motivate the paper by showing you guys some of the behind-the-scenes work we do at Curalate. And then we'll dive into some of the prereqs. We'll talk about approximate nearest neighbors, which is the generalization of the algorithm. Get everyone on the same page. Then we'll dive into the paper, which is really a contribution on top of existing work. So we're actually going to go through all the existing work as well. Don't be scared. I tried to make it pretty fast. And then we'll wrap it up. I'll show you some use cases and software and some of the cool stuff we did at Curalate. I tried to structure this talk in a way that we kind of explore the problems through data. We try to answer problems with data at Curalate, so I tried to do the same thing here. And hopefully that will make the intuitions behind the contributions clear. So if your eyes glaze over with the math, but you get the pictures, we're all fine. That's where we need to be. Cool, so Ted already introduced me. He already talked about all the beer brewing stuff. I'm a research engineer at Curalate, and what that means is I kind of bridge the gap between scientific researchers and software developers. Being at a software startup, it means I also wear a lot of hats. So I kind of do some data analysis, some data science as well, occasionally the PMing. And most of what I spend time on is addressing problems of scale. Things that work in the lab don't work in the real world, usually because of the problem of scale, whether it's scale of variability, scale of data, or scale of accuracy. So what my job is to take existing research and build it into products in Curalate that gives them a competitive edge. So I develop intellectual property, right? And usually that means taking a paper and figuring out why it doesn't work with our data and then making it work with our data. The paper we're going to talk about today is a really good example of solving a problem of scale. So it was really valuable to us. Before I dig into the paper, we got to thank Curalate for the pizza. And it's required I mentioned that, yeah, we're hiring. So we're looking for software engineers, product managers, and product designers on our dev team, as well as a bunch of other stuff. We're a Philadelphia-based startup. We started here in Philly at somewhere on Locust Street. It was a terrible place. We're in a much cooler building now on 24th and Walnut. We also have offices in New York City and Seattle. We have venture capital funding, so people are getting paid. Nobody's doing anything like that. And we're hiring, so if you're interested, please drop me a line. And what we do is we like to power discovery through visual content. So we connect social and content marketing with e-commerce at scale. And I can see all of you. What? It's cool. You're not marketers. I'll show you a really easy example. This is Urban Outfitters' website. And this is what we call a fan reel. This is powered by Curalate. These are user-generated photos that users uploaded to Instagram. Our software finds those photos for Urban Outfitters, asks the users for permission if Urban Outfitters are interested in it, and powers the technology that lets Urban show that on their website. The reason this matters is that user-generated photos are driving sales. And to drive sales, you need to be able to go from this picture, to the products that are in it. So if you go to Urban Outfitters' website and you go to the UO community page, you can click on any of those photos and go to the product page and buy it. And all of that API is hosted by Curalate, and all the dashboard technology is stuff that they're logged into. So to make this work, and by work I mean make money, because We all know eventually at the end of the day we have to make some money. We have to answer a reasonably simple question that's really hard to do. And that's, given a user-generated photo, what products are in it? Once we know what products are in it, we can put it on our client's website for a fan reel. We can have them post it to social, all these different things that our software lets them do. But we first have to answer that question, what products are in the photo? And the first version that we did this with Curalate just required the client to know their entire product catalog. So if they wanted to tag that hat, they had to know that it was a Collins felt hat. And I would never be able to remember that. And some of these clients have, we work with some of the largest brands, e-commerce brands in the States, and some of them have millions of products. So it's really hard. And it also means whoever's doing that tagging, which we can all be honest is an MTurk task, needs to be somebody who's very familiar with the client, so they have to be trained. What we'd like to do is, instead of saying, hey, why don't you tell us what product that is, we'd like to help the user out and recommend products to them. Identifying that exact product is very hard. It's a hard computer vision problem. Identifying similar products that look like it is also really hard, but it's a little bit easier. So that's what we want to automate. We want to be able to say, like, hey, you got this user-generated photo. We think this product is in it. Right? So we built this. This is an example video of our version 0. They open the user-generated photo. We detect the products in there, and we recommend what products we think is in that box. The user comes in, clicks, yeah, it's that product, moves on, publishes it to the website. They make money, we make money, everyone's happy. Right? So we're keeping the user in the loop. Sorry, this is a little washed out. We're keeping the user in the loop. That gives us a little bit of feedback, and it makes sure the client doesn't have any wrong products. So I'm going to show you a little bit about how this works. So on the data side, we have a few pieces of data. We have the product catalog. Our clients give us all the photos of all the products they sell. There's like a few million of these. This is our reference set. We'll get a query image at any time that has a user-generated photo, and we need to recommend what products are in there. Yeah?
So when you say offline, that means like the company ships you.
Yeah, they have a CSV or JSON or Google feed. We hit it periodically, or they tell us to process it. We can process it offline. When I say online, that means the user opened to that photo in that view you just saw, and I need to tell them what products are in there. So I kind of got to know ahead of time. Now, Instagram sees millions of photos a day, and we see a good chunk of those. So doing it offline as we see Instagram photos is pretty infeasible, right? Especially since our clients are only care about a really small fraction of those Instagram photos. Does that make sense? So this is a web service we need to build to say, hey, you give me that photo, I'll recommend what photos are in. So how we do that is first we detect the objects in it using some nifty computer vision. And that'll tell us, okay, there's a skirt here, this is a dress, things like that. I'm not going to get into that part. And then we take those objects detected parts and we put them through a convolutional neural net. Now this is where the deep learning comes in. This is the thing everyone's really excited about. This is not what we're going to talk about today. Okay. I am happy to give another talk about that. If someone else takes over papers we love for tech. So we push this through the neural net. What you need to know about the neural net is it spits out a very large, high-dimensional vector that represents the semantic content in that box. All right? So the query vector gives us a 2,048-dimensional vector of floating point numbers. Every box in our reference set gives us the same size vector. So now we have these reference vectors y and our query vector x. And we want to search for the ones that are closest together. I'll get back into that. Well, I'll show you in a minute. So all we have to do to search for that is to find the one that's closest in the Euclidean space. You can use other distance measures, but we're going to use Euclidean because that's what all the literature uses, and that's what we use, and that's what everyone's used to because you can think about it on a graph, and you learned it in third grade. Right? So if I want to match that skirt, all I have to do is find the reference vector that has the closest distance to my query vector x. We're going to spend all day on this. Sorry for the deep learning. All right? So this problem is called nearest neighbor. I have a reference set, and I want to find the nearest neighbor to my query x. Let's look at that a little bit more detail, because it'll help us understand the paper. So if you guys know nearest neighbor, get some pizza, get some beer. If you don't know nearest neighbor, hopefully you will. So the regular nearest neighbor problem is pretty simple. Given a query vector x, shown in green here, I want to find the closest vector in the reference set We'll denote that by y, where closeness is defined by some distance measured here, right? And we're going to use Euclidean distance, right? And if we were to do this naively, it doesn't sound too bad. I compute all the distances of all my reference vectors to x, yeah? And then I take the minimum one, right? Makes sense? Everyone's cool with that? That's linear. The complexity of that is linear in the space of the reference set, right? It's big O of n. Everyone remember asymptotic behavior? If you don't, hopefully you will by the end, right? I have to look at every vector in that set. That's what that means, right? So that's, okay, we'll come back to that. But we want to show a number of different results, right? Like, they want to search for that skirt. They might, the first one might be wrong because the neural net didn't do its thing, or there's some occlusion, or something else is good. Vision is hard. So we want to show a few different results, and that's known as k nearest neighbors, meaning I want to find the top k neighbors that are closest to that, right? Which means I run nearest neighbors, and then do it again and again, or I sort the list and pick the top k. Everyone comfortable with that? The complexity of the naive algorithm there is n times log k. Why?
You basically have to do it k times.
Yeah, that's true. So you could do it like,
there are a couple different ways to do it, but yes.
well, where's the log k come in?
The log k comes in the fact that, well, you have to do n to find all the distances.
Yeah, you have to do n to find all the distances for sure.
And then the k is in the minimization sort that you're doing. So it's a little faster because you're only saying, well, let's take the k shortest. So you can basically take the first 10 and then knock one out or something. It depends on your algorithm.
Exactly. So if k is 10, you're totally right. I only need to sort those top 10.
Right.
That's where the log k comes in. We'll see exactly how that works in a later slide. So this is the naive approach, right? It doesn't sound too bad, right? But will it scale?
No.
Why won't it scale?
Because you need.
Oh, sorry.
Well, there's another number that you left out, which is like the dimensionality.
Yes. You're exactly right. The dimensionality of the vector means that distance is not free.
Right.
The dimensionality is really high, so I have 2,048 of those.
2,048. It's not.
It's not free.
It's a constant value, but it's a big constant.
Yeah, I mean, I'd be lucky to get it all in L1 cache, right? What's the other reason it's not scalable? What were you going to say?
Well, because you need all the data at one time. You need
it's
10 versus everything.
Yeah, it's not space scalable. You must have read ahead on the slides. We're going to get
No, I'm a geek.
You didn't read the paper.
N is
No, I totally
N
didn't
is
look at
pretty
the paper.
big.
Okay, I didn't read the paper.
I hope you didn't read the paper because I'm supposed to explain it. Otherwise, I'm wasting my time.
Shit, I read papers all day. I don't even meet other geeks.
Yeah, we're here to drink beer and eat pizza.
Exactly, and with that I need a beer.
Yeah, so D is big, right? So the distance is not free. And N could be pretty big too. Like I said, our clients might have like millions of photos. So this will take a long time. This is where approximate nearest neighbors comes. Approximate nearest neighbors is a nearest neighbor algorithm that doesn't promise you're getting the closest ones. It just tries to find ones that are close to the closest ones. It trades off accuracy for speed, or space, as we see. It's commonly measured by what's called recall at k, meaning I take the k nearest neighbors, and I take the k approximate nearest neighbors, and if the right one's in there, I say, yeah, you're good. Recall at k is the number of queries with the correct answer in the top k results. So what that means is for every query vector I have, I go and say I get 5 of the approximate nearest neighbors. If it's true nearest neighbors in there, then I get that one right. The recall at k is the percentage of queries I get right. So if my approximation technique is working perfectly, recall at k is 100%, or 1. Everyone comfortable with that? Cool, so that's how we're going to measure this. This is a well-studied problem. Here's a brief overview of the Wikipedia page. Yeah.
Is there a generalization of that where you have, instead of saying it's the top 1 nearest neighbors, there you have the top L nearest neighbors?
Yes, and we'll see that in the results.
Oh, okay.
Because often you say, okay, what's my recall at 1? What's my recall at 5? What's my recall at whatever? Right. So yeah, good question. Yeah, so we'll see some of that in the results. So this is a brief overview of the related work. One way to tackle this problem is through tree reinforcing. It's like KD trees. Are you guys familiar with KD trees? Some of you? Okay, so KD trees is the higher dimensional generalization of binary search, right? If I were to do this in 1 dimension, I'd sort that list, do a binary search, get my nearest neighbor in log n time, right? That'd be really fast. KD trees does that. but it doesn't work as precisely. So that was an early algorithm. We still need to store all of the vectors to do that, right? A few other common techniques are neighborhood graphs. These are getting a lot of attention because they're really fast and really accurate. But we have to store all of the vectors, right? Locality-sensitive hashing, which I'm sorry that got cut off, is another technique that also got really popular about 5 years ago. But it still needs to store quite a bit of data. And its query time, while good asymptotically, is not good in practice. So these are asymptotic query times. There's some constant here that matters to me as an engineer. Yeah?
No.
Oh, sorry. That matters to me as an engineer that might not matter to a scientist. Right?
What's rho there, or does it?
Rho is the likelihood of the hashes colliding. Yeah, I tried to be precise, but I'm not going to. Like, I looked into locality-sensitive hashing for this problem, and it wasn't good. So the technique we're going to talk about today is quantization. Quantization gives us sublinear storage and sublinear search. I say sublinear because the actual asymptotic cost depends on your approach and on your data. So you might be saying, like, hey, like, why does sublinear space actually matter, right? So let's look at this. How bad is it, right? So this is a graph here where I show the number of reference vectors in the data set. So it goes from 0 to, like, I don't know, a lot, right? And D, our dimensionality is 2048, right? That means if those are floating point numbers in 32-bit representation, each vector is 8 kilobytes, yeah? Which means I store 130 of those in a gigabyte, and I'm quickly at 8 terabytes when I hit 1 billion images. And I can hit 1 billion images, right? It'll happen. We're not there yet, but we're getting there. Just 1 million images is 8 gigabytes, right? You say, hey, man, storage is cheap. What's the problem? Well, I say, I need all of these things at search time to look through, right? So how cheap is it? Well, I can put a dollar value on these by looking at AWS costs, right? So for 50 million images, I need an M5 24XL, which has 384 gigs of RAM, which costs me $3,300 a month, yeah? And Amazon, thankfully, scales their cost linearly. So regardless of what instance I pick, I'm paying 7 cents a month to store 1,000 images. Say, that's not so bad, and I'll say, well, I need to store a lot of images, and we're a startup, and we need to save a little bit of money, and this will get out of control really quickly, right? The point is, this isn't great. And it's our biggest scaling factor is actually the storage. The search of all of those things was sublinear. We'll see how to do sublinear search. It's not that bad. But storage is what's holding us back. This also doesn't cover the cost of getting that data from whatever cloud storage I have onto whatever machine is serving these requests, right? Like if I do an ASG, who's familiar with AWS? Okay, so if I launch up an ASG, auto-scaling group, and I have these hot instances that turn on and off depending on my query load, and I got to copy 384 gigabytes off of S3 onto the instance on boot, it's going to take that thing 20 minutes to start up, right? Like it's going to be slow. So that's not even taking that into account. That's an extra complexity. All right, so let's talk about how we do this. So locally optimized product quantization is the paper we're going to discuss today. This paper is from, I think it was 2014. It was presented at CVPR, which is one of the premier computer vision conferences. It's fun to go if you've never been. And it's actually a simple contribution on top of existing work, which is one of the reasons I like it. But to really understand its contribution, you're going to have to understand everything else. So we're going to start at the end with what quantization is. And then we're going to build our way up to what locally optimal product quantization is. This is the worst math slide in the deck. Maybe the second worst. There's one that's worse. Okay, so a quantizer is a function that takes one of our vectors, y, and returns another vector from a set in the same space that has a smaller cardinality. That's that has. So what am I saying? If I have one of these red vectors here, the quantizer will return one of these blue ones, right? It'll return the one that's closest to it given my distance. So for any of these vectors, my q of y, if this is y, q of y would return this guy, 2.1, 2.7. Make sense? Yeah?
What's the little arrow with a line on it?
That means it maps to, I believe. That's what the LaTeX command was /map to. So I'm assuming that's what it means. Good question. Don't call me out on too much math. So you might say, hey, why are you doing this, right? And the reason is the number of centroids I have, the centroids are the values the quantizer can map to, is going to be much smaller than my data set. Okay? So I'm going to say, hey, this example, I have 3 centroids, and my quantizer function q will take one of these vectors and map it to one of those guys, right? And the way it does that is it just picks the one with that's closest, the minimum distance. And it doesn't escape me the irony that that's what we're trying to do in the first place. Right? So this is an example, a very crude example of a machine learning technique where I might say, hey, I have a data set. How do I pick my centroids?
You're just bidding like a mode function, right?
Yeah, that's exactly what we're doing. We're binning. Quantization is another term for bin. I'm taking something that's floating point, I'm making it an integer. Right? Yeah, this guy, all of the, you can draw a line, we'll see it in a minute. This bin gets represented by that guy, right? And we'll see why this is good and then why it's bad, and then why we make it better. So to find, say I have this data set, and I want to pick my centroids, right? I have this, and I say I want 3 centroids. I want to pick the centroids that best represent the data. And this is done through an algorithm called k-means. Does anyone use k-means? I know Wall has, yeah. Cool, great. Enough of you have that I can glaze the slide a little bit. K-means picks a few of the points at random, or maybe not at random, if you're really smart. And then it assigns all the points in your data set to the closest one. Then for each group of assignments, it takes the mean and repeats. It's an iterative algorithm. It has been shown to find the optimal quantizer, however. So it works really well from that point of view. But it's iterative, so it takes a long time. But we're still going to stick with this. We'll see why it's good and why it's bad. So k-means, given the reference set, will give us the centroids we want back. You have to tell it what k you want. There's a whole other area of study that tells it, how many centroids.
Do you know what K should be in your application?
I do know what K is in my application because I plotted it on a graph and said, that's the one. You plot costs, you take supply and demand, and you're right there, right? So it's exactly how you do it. Yeah, we data-driven decision making. It's awesome. Okay, so let's say I do this, and I set K equal to 3. Then my quantizer effectively carves out my space. It bins it, right? So this is what's called a Voronoi diagram, where I've drawn a line that segments the space. Everything on this side of the line gets quantized to that guy. Everything on this side gets quantized to that guy, right? Once I've done this, I can build an index of my images that only stores the quantization value. Not even the centroid, just the number, right? So my first image, image ID 1, I'll quantize. It says, hey, you are in the first centroid, right? That's all I want to store on disk, is which centroid I got assigned. Yeah? I do that for all my images. Why would I do that? Right? Because if I do that, I can represent the entire reference set in only log 2k bits per vector, right? If I have 8 centroids, I only need 3 bits to represent 8 different numbers, yeah? That's all I'm saying. And I say, okay, for all my images, I find the centroid, I write that number to disk. Right? Super compressed. Great. Now this isn't free. When I do that, I've lost the data that tells me the difference between all of the guys in each cell, right? So my error, which we define by the distortion, is the distance between each reference vector and its centroid, right? That's the data I'm throwing away when I quantize. Yeah? I'm getting lots of lower space, but I'm throwing this data away, which means I really can't tell the difference between all the guys in this bin. I only know that they're in bin 2, right? Makes sense? Cool, but that's okay. We'll come back to why that's good and why that's bad. It's something to keep in mind. So if we do this, let's say we were to store just the quantized values, and I want to search. I want to use this for approximate nearest neighbor search. This is the fun part. Okay? So I have this query vector x. I'll come back to that. First, I'm going to take that query vector and compute the distance to every centroid in my quantizer. And I'm going to store that in a map, because maps have, what's the lookup cost? Constant, what?
It depends on the type of map.
Okay, it's an array, because these are numbers, right? So lookup's constant, right? Cool, so I store that in a map. Then I go to my reference set and say, hey, for the first guy, he's quantization value 1. So the distance between x and my neighbor, image ID 1, I just look it up in this cache, right? It's 0.4. And I throw that into a max heap, right? We'll see why that's awesome. Then I do the same one for the next one. I say, hey, okay, distance to this guy's 3. I throw him into the max heap, right? I do that for all of them. And whenever my max heap gets bigger than k, the number of neighbors I want, I pop the max off. That's where the log at k comes in. Makes sense? Every insertion into this max heap takes log k. I got to do n of them. Getting the distance is constant because I pre-computed the sentence, right? So this sounds great, right? It's still linear, but it's a fast linear, yeah.
So just to tie it back a little bit, so finding the centroids and building your reference set, that can all happen.
That all happens offline.
Yeah.
I get the product catalog.
Right.
I build the quantizer. I build the reference set. I store that reference set in some blob in my object store.
Right.
Then at query time, my service loads that thing. It does this algorithm.
Yeah. And
which
so
is pretty
the
fast.
query vector X is the online.
Yep, that's the online.
Okay.
Yeah, good question. I avoid more service talk through the rest of the talk because the paper's hard.
I don't know.
Cool. So what's the problem with this? Well, one problem is it's still linear. That's okay. We'll come back to that. The other problem is like, hey, I can't tell the difference between these two guys. They have the same quantization value. I threw away their distances when I quantized, right? So if I'm searching for x, if image 3 is the true closest one to x, I can't tell the difference between image 3, 2, and 6, right? They all go to the same value. Because I've taken their centroid. I'll show you in this picture. Like all of these guys, I only know the centroid, right? So they all have the same distance. So we'll come back to how we can handle that. But in the paper, we actually ignore it. We assume we don't deal with that. And we'll see why it still works. So that was linear, right? So I had this linear search. I still have big O of n k, right? I want to make this sublinear. I want it to be faster. So one way to do that is build what's called an inverted list. And then we'll take the query vector x, and we'll actually quantize it. And then we'll only look at images near there. So what's that? I take the query vector x, I quantize it. It says, yo, you're closest to bin 1. And then I only look at the images that got quantized to bin 1. Make sense? Now it's sublinear. If I have a good quantizer, it's n divided by k, roughly. Yeah. This is what search engines do. When you type in the word cat into Google, it only looks at documents that contain the word cat because it has that inverted list somewhere in their MapReduce archives. Right? So this is a known technique from search engines. It works. There's a slight problem with it in that, yeah.
So then, if I'm understanding this right, I'm not sure that
No, it's totally okay.
That you only ever kind of pick points that are close to the blue dots. And
Yep.
So maybe the thing you're looking for is like where that green dot is, near the X.
Yeah.
At the bottom, and
Yeah.
you kind of return that.
Good job,
Right?
Walt. Yes. The problem with this is known as the edge problem. This is my query vector x. Its nearest neighbor is in a different cell, right? So this gets worse as the dimensionality gets higher. So they handle this by saying, hey, okay, I'll quantize this query vector x to bin 1. But I'm going to look at the next, 2 or 3 nearest neighbors and look in their cells too. It's still sublinear, and if your quantizer is big enough, you still get a good speed up, but you avoid this problem. It's not possible to avoid it entirely, which is why it's an approximation technique. Right? Cool. So good observation. Literally on my next slide, I said, hey, what happens there? I skipped over one slide, and that's, as an aside, again, the paper doesn't do this, we're not going to do this. If you want to store all of your vectors on disk, you could pull out this inverted list and pull out the actual vectors and just compute the distance on those, right? So I could re-rank that by the true distance and then get a better result, right? This requires linear storage. I brought it up in the slides because it's a known technique that people do. We're not going to do this. We don't want linear storage, right? We already saw all the executives in the room lost their minds at 7 cents per 1,000. Okay, cool. So that's one way to re-rank. We saw the edge problem. You can combine those two, inverted list and re-ranking. It's pretty sweet. You want to look at the W nearest centroids to avoid the edge problem, which means our search time is now W times n divided by k. That's our approximation. Not bad, right? So whether or not we re-rank, let's assume we're not re-ranking, we're going to get some great quantization. Yeah. So the whole point of this was we wanted to reduce our size. So I generated a synthetic data set and then computed how much space we save. But actually, I didn't need to because it was just algebra. So I just graphed it, right? So this is an example of how much data we're going to save by quantizing. So each of these lines represents a different data set size, from 1,000 to a million. Yeah, no commas in there. On the bottom is the number of centroids, k. And on the left is the compression ratio, which is the size of the uncompressed set divided by the size of the compressed set. So higher is better, but all of these are pretty high, right? Look at n equals 1,000,000. If I use 1,000 centroids, I compress over, I wrote it right here. For 1,000,000 images, if I compress with 1,000 centroids, its compression ratio is 170. That means the compressed size is less than 1% of the uncompressed size. So compression is good. Quantization has something going for it. The problem is, I need a lot of centroids for it to be accurate. So here I show on the left how many centroids I would need to get a recall at 5 of 90%. That means 9 out of 10 times the top 5 have the true closest neighbor, right? And I did this for a few different dimensionalities. And on the bottom, I show the size of the reference set. So at 10,000 images, if my dimensionality is only 16 floats, I need 5,000 centroids for this to work. That's half the size of the data set. At dimensionality 128, I need 10,000. Like, I haven't saved any work, right? But you might be saying, come on. Like, half of it's still good. These are big numbers, right? So that's how many. So needing a lot of k is only part of the problem, right? Because you could say, like, you could make the argument if you have 1,000,000 images, just make like 10,000 centroids and deal with it, right? You'll still get a low compression ratio. It'll still be great. Well, k-means is iterative. It's not closed form. So it has a pretty big computational cost. The asymptotic running time of k-means is n, the size of the data set, times d, the dimensionality, times k, how many centroids you have, times the number of iterations you do. That's true, I got it off Wikipedia. So I plotted that number of operations for a few different sizes of k as a ratio of n. So this purple line is the one we're just looking at. Let's say k is like half of n, right? You can see this is exponential. It's actually close to n squared, because if k is a constant times n, it is n squared, right? So the number of operations are really bad. So quantization has some good things going for it, in that we get really high compression ratio, only n times log 2 bits per vector, right? We can do fast searches on the cache distances by using our little lookup trick, yeah? We can do sublinear searches with inverted lists. But the con is, like, it's way too computationally expensive to do this in reality. It's a scaling problem, right? Like, it won't work. If k is significantly less than n, which we need in order to actually run k-means, we're not going to get unique results there, right? You know, it's just not going to work. Right? So quantization, yeah.
Does k have to be, like, what's the relationship between k and, like, the number of images you might be searching for?
Oh, yes, good. Sorry, I meant to call this out. So k has a few different meanings in this talk, and it's not my fault. K, in a quantization sense, is the number of centroids. The literature has agreed upon
right,
that.
That's what you've been talking about. But
the recall at k, that's the number of neighbors, and they're separate. They're not related at all.
Right. But so if Urban Outfitters has 1,000 things in their inventory that you might want to search for, does k need to be 1,000?
No, it doesn't.
It needs to be.
It needs to be some good representation of the reference set.
And because you're looking at multiple centroids, you can get. You end up picking more than just 1,000.
Yeah, right. So I do choose k when I run k-means, and that's great.
Right.
Okay, so quantization. Good space compression, bad computational complexity, because we need a lot of centroids. That's where product quantization comes in. So product quantization is a paper in 2011. It was published to PAMI, which is a really cool journal, which I don't read enough of, but it's a good time. And they had a really interesting idea. They said, hey, all right, let's take our reference vector y. This thing has 2,048 dimensions, right? Instead of quantizing that, I'm going to split it up into m subvectors and build a quantizer for each of those, right? So each of these has a dimensionality of d divided by n, right? If this thing's 2,048, and I make M2, each is 1,024, right? And then I build a quantizer for each of those, right? Why? Why does this help us? Any ideas? It's cool. You're not supposed to know. It's a rhetorical question.
You could search them in parallel.
Close. If I do this, let's say I do this, and the number of centroids I use for the quantizer for the first subvector is k prime. We'll make it 120. Right? Let's say I split this into two. We'll take a simple example. I split this into two. The top half, I do 128 centroids, and the bottom half, I do 128 centroids. Right? Then I represent each of those reference vectors by the two centroid codes. How many feasible centroids do I have total? 128 squared, right? It's combinatoric. It's the Cartesian product of all of the possible centroids. Does that make sense?
Yep.
So this guy could be 0, 1, 2, up to 128. This guy could be 0, 1, 2, up to 120.
So a code book is a set of centroids?
Yes. Code book. Oh, yeah, sorry. Good eye reading the slides. Yeah. So sometimes I get ahead of myself. Right. So the code book is the possible centroids that we have. The size of the code book for product quantization is k prime, which is the number of means I use in my k means on each subvector, to m. It's the power of m, right? That's awesome. And I can run k means even faster if the dimensionality is less, right? And in fact, we'll see we don't need a big k prime for this to work. We make a bigger m, everything gets better, right?
Does every single section have to have the same k?
It helps if it does, because then you can bit pack it better, right? Otherwise, I'd need to remember the first. No, theoretically, but in practice, everyone's like, give it 128 or 256. Let it do its thing. Yeah.
So when the product quantization is a debt multiplication?
Yeah, the product comes from the fact that the code book is the Cartesian product of the sets of each subvector's centroids. Yeah.
So if you have a very large number of centroids,
Yeah.
like is it large enough it's approaching the original data set cardinality?
It could even be bigger.
Is that not bad?
We'll see. So let's look at the. So we just pick k and we pick m. Here's a toy example. This is a data set where d is 2. K prime is 3. Each dimensionality is going to get 3. M is 2, which means I'm basically doing this on both axes. Yeah. I get this interesting grid structure, right? Because you can think about this as I basically put all these guys on x, ran k means, and got 1, 2, 3 means, right? I put all these guys on y, only took a y value, ran k means, got 1, 2, 3, and then the Cartesian product is the splatter of that set. Right? Makes sense? So you get this interesting grid structure, right?
But those
But-
aren't the clusters, though.
What's that?
Those aren't the clusters you would get if you ran k-means.
Those are those clusters I would get if I ran that on that data, because I actually coded this and ran that on that data.
No, but if you ran it in both dimensions at the same time, are those really the clusters you would get?
Yeah.
Why?
Oh, yeah. Yeah, so it took me a long time to understand why this happens, right? So think about the fact that these are two-dimensional points, right? When I run k-means, I'm running it only on the x's and only on the y's. Make sense?
Does it work the same way if you code for no matter how much dimensions?
It does, but I can't visualize that many dimensions
Yeah, yeah.
because
If it works for
I'm not
two,
that
it'll
lazy.
work for many, probably.
Yeah, you get some kind of gridding effect. Walt just got the why it's a grid.
I think
Yeah, so imagine all of these points in only one dimension. Like if they're only on x. If I put them all down here and I ran k-means, I get 1 here, 1 here, and 1 here. Does that make sense?
Yep.
Does that make sense?
I think
That part makes sense, and I understand how you're getting the grid. What I'm not convinced of is if I ran the k-means optimization from scratch in 2 dimensions, that I would get that regular pattern of grids. I would imagine
No, you
that
wouldn't. You wouldn't.
That's
Oh,
Yeah,
okay.
you wouldn't.
I
That's
wouldn't.
yeah.
Good.
No.
Good.
In fact,
Okay.
you would get a better result
Yes.
because you wouldn't have this regular pattern. You'd get them closer together, but we've already decided we're not going to do that because it's too computational.
But you don't care.
Yeah. Right.
Yeah.
Like, does that make sense? I have a
Sure.
good figure of that later, and I'll call it.
Yeah, that's fine. I mean, you got a different grading system that's a little less computational.
So what is
Yeah.
M in the upper left hand? Why is the blue dot on top of the
Why is this one up here?
There's only 1 point.
Yeah. Good question. Why does that happen?
First of all, what's M equals to? What is
M is 2 here. So M is the
That's in
number of
dimensions,
breaks
yes.
I have in the
Then
subvector.
what's D?
D is the dimensionality.
So then what's that?
M is how many how many subvectors I break it up to. So if D is 2048 and M is 32, each one becomes 128, 30, 64, 64 dimensions. Let me give an easier example. If D is 16 and M is 8, each becomes a dimensionality. Each subvector is a dimensionality of 2. Does that make sense? M is how many subvectors I get after I break it up. Cool. Everyone got it? Okay. If you don't understand the rest of the talk, I'm happy. It just gets worse. Okay, so let's compare what happens here. So from a complexity standpoint, if M is 1, it's just regular quantization, right? So I've shown a number of operations it would take to do that on this dotted line. And then I've shown the number of operations it would take to do for different values of M on these solid lines. And you can see when M is 2, meaning the next complexity level down, I'm only breaking it in half, right? M is 2, I'm cutting it in half. I still get significant savings on the computational complexity. Okay? Like this is going to run a lot faster. Make sense? So we're already doing better. And as M gets bigger, it just gets better and better. Right? Everything's going well there. If you make M too big, you might end up with too many. Yeah.
And so the reason why that is because just running k-means has like big O of n squared or whatever, right?
Yeah, exactly. Right. Because this is almost an n squared curve.
Right. Yeah.
Okay. Cool. Okay. So let's look at what happens. So we can take this technique. It's creating centroid codes. And we can use all our same tricks. We can do inverted lists, and we can do our pre-computed distance accuracy, right? That's the fun one. So what if we did that? So here I show the number of centroids needed for our regular quantization, which we saw went up pretty high, yeah, and for product quantization for different M's. So on the bottom here, this is the reference set size, and on the left is the K prime needed, and I show for a few different values. You can see I need way lower values of K prime because I'm taking K to the M number of centroids, right? This is awesome. Okay, so we solved a few of our problems, right? Now you might be saying, hey, this sublinear search could be kind of hard. Yeah. You can do inverted lists with this, but then you kind of have this different weird quantization problem where either your inverted list is the size of your Cartesian product of centroids, which is really big, right? Or you're going to say, I'm going to make an inverted list off of each separate one and put all the vectors in M different lists, which is what the original paper did. Both of those will work. There's been some other work that does an even better job. And we'll cover 2 of these techniques just because I'm not going to get too much into these. They're kind of conceptually simple, but they're used in all of the papers to compare the results to other techniques. Okay? So
the word product here is referring to that
Cartesian product. Yep, exactly. That's some good marketing from them.
Yeah, that threw me off when trying to read the paper.
I know. Everything about that paper threw me off, and then I hated it, and now I love it. So hopefully you'll love it by the end of the talk. Okay, so we've been looking at this picture all day, and it looks pretty normal. And in a lot of papers, we assume a normal distribution. But IRL, data is usually multimodal, right? Things are going on. Some smart guys said, hey, why don't we use that fact to partition our data? Instead of doing inverted lists, we'll just try to break this thing up ahead of time and then search each group. Right? And they did this with what's called a coarse centroid. So a coarse quantizer. So they built 2 quantizers. The first one, they just run k-means with a really low k on the raw data. So here I've run it for k equals 5. The means are shown in green, right? And that tells you, hey, like, I've got this really coarse quantization. It's not going to help me with my distance. But if I do that, and then I store each of the sets that get assigned to each centroid on disk in some way, right? Then I can just search in that guy. Right? It's the same thing, yeah.
So the dimensions of this, it's like 1,028 like channels
from the neural net. Yep.
So if you pass everything through the neural net, you still find these different modes like that?
Yeah, you do. It's harder to see them because they're there. Yeah. And even if they're not, we all know throwing extra variables at the problem will get better results, right? So, hopefully, in theory. So the coarse quantizer, we run k-means on the thing with a really low k. And then we assign each reference vector to the cell with its closest coarse centroid. Then you run product quantization, and this is the really fun figure. If you ran product quantization with n equals 8, we get this grid-like structure again. You'll notice a lot of them are getting nothing, right? We're going to come back to that in a bit. But I can run product quantization to store the reference vectors on all the ones that are closest to that. Then when I get a query, I say, which one are you closest to? And I only look at those guys. That's where the sublinearity comes in. So it's n divided by big K, where big K is my coarse quantizer. Simple approach, right? Not that bad, yeah? Still have a lot of empty dots here. This is a foreshadow of the future. Some other guys released this paper called inverted multi-index. And they said, let's do the same thing, but my coarse quantizer will also be a product quantizer. And everything blows up. And this is a really cool paper, and it's really important, and I don't have time to go into it today, but that's the general idea. Is I make a coarse quantizer that's a product quantizer, then I put everything in there with a smaller, finer quantizer. Everything gets super fast, and we can suddenly search on billion-scared data sets. It's awesome. So we'll see this in the result papers as well. Okay, so back to regular product quantization. That's an aside of how we do the sublinearity. So this is the results from the actual product quantization paper. They compare their technique, shown in blue here, to a hashing technique, shown in purple, and a few other hamming embeddings, which is another hashing technique, shown here in gray. You can see the blue is upper to the left, which means it's better, right? Now, this is a recall at R curve, meaning over here, R is on the bottom, meaning they're looking at the recall for the first nearest neighbor, right? Who asked about this earlier? Okay, yeah. So what they say is, hey, what's the recall at 1 for all of these techniques over this million-scale data set? And recall at 1 for all these techniques is somewhere between 0 and 40%, right? Well, what's the recall at 10? Let me plot that. Then the recall at 100 and see how it goes. A perfect technique would just have a bracket-shaped line, right? Makes sense. This is a great way to compare approximation techniques. They also compared it with the coarse quantizer of their own technique. And you can see when W equals 16, that means they're hitting 16 of those coarse quantizations, shown in green. They get a really good result. State of the art. Pretty cool. Not super great from an application developer because I need to show 10 results just to get 70% accuracy, right? So I'm reading this at work, and I'm like, this is cool. Seems like it'll solve our space problems, but it's not going to be very realistic. Right? The neural net's bad enough. Yeah. Like, computer vision is hard. We're going to make it worse. Right? But it's a great result for the product quantizers, moving the thing up. So just to wrap up product quantization, the idea is we break that vector into m subvectors, which have d divided by m most around. Right? So 16, if d is 16, we break it into 8 different things. Each subvector has 2. We run k-means for each of those guys separately. That gives us a huge number of centroids, even though they're kind of distributed in this regular grid. But we still get some great storage costs, right? It's n times m log 2. So everything is still compressed a lot. Awesome. We can still do sublinear search with a lot of our tricks, and everything's going great. But it's not that accurate, right? We saw on that accuracy curve, we're still not doing so hot there. So the question was, well, can we do better? And these gentlemen came in 2 years later and said, yeah, we can do better. We'll call it optimized product quantization. The idea here is pretty simple. Let's look at that grid again. There's a lot of space. There's a lot of centroids that aren't going to get any nearest neighbors, right? These are just wasted. Yeah. So they said, well, hey, could we align these better to the data, but still do product quantization? We still want all the speed. We just want to maybe rotate this or squish it a little bit. Do some of that fun math stuff too, right? And they said, let's take a hard, rigorous look at this. And let's go back. Do you guys remember the error we measured, the distortion? It's the difference between the vector and its quantization center, right? So they said, let's take that equation, shown here. It's the sum over all the vectors in my reference set, which is the difference between the reference vector and its quantized value. And we're going to insert this matrix R. I'm going to insert a matrix R that just projects it, right? And I'm going to say I want this thing to be positive semi-definite, which means it's transposed times it's transposed as its inverse, it's transposed times itself as its identity, and it's square. Everything's happy. You can invert it, all that fun stuff, right? So this is the equation I want to solve. I want to pick an R, given my data, such that I minimize the distortion, meaning I make it as low as possible, and is subject to the fact R will be positive semi-definite. Right? And we're going to assume that the data is normally distributed with a zero mean. This is a bad assumption to make, which is why we have another paper after this. Right? But the zero mean part isn't that bad. I can compute the mean and subtract it and store it in my pre-processing step, no big deal. Normally distributed part, not so great. But let's assume that it is for a little bit. Right? So the paper is pretty in-depth, so I don't want to like cover too many. I don't want to cover their proofs, because I only partially understood them. But they had two criteria for solving for R. First is that each of the subspaces of the vectors should be mutually independent. And the second is that if you balance the variance between those subspaces, so if you have both of those criteria, meaning that you have mutually independent subspaces and you balance the variance, they showed that solving for R in that case would indeed minimize it. So they said, hey, if these two things are true, then if you pick an R that makes these two things true, then you will minimize your distortion. So that's the proof I'm deliberately glazing over. All right? So please just trust me on that one. What's great about that is they came up with two algorithms that could do that. One was a non-parametric technique that was computationally feasible for large data sets, but they showed did really, really well. The other was a parametric solution, which is pretty elegant. They just said, let's just make these two things as true as possible, right? So they said, let's look at this first one, independence. How do I make my subspaces mutually independent? Well, there's a really good known technique for that, where you do PCA alignment. And you mean center the data, that's cool, gets us to zero mean, and then you rotate it to the axis. Okay. And for the second one, they permute the rows to balance the variance. So let's see how they do that. So they essentially apply this technique to make these things true to solve the problem. Right? So let's see what goes on. Okay, so who remembers eigen decomposition? Thank God. Because I made this slide and was like, this is the worst math slide. Okay. So let's say we have this data. I'm gonna glaze over this part a little bit. We have this data here. I'm gonna compute its covariance matrix and then do eigen decomposition, which only works on square matrices. That's okay. Yeah, it's PCA. Exactly. Thank you. So I do PCA, which for those of you who don't remember it, means I mean center the data, then I rotate it around its primary axis, right? Eigen decomposition can be used for PCA, and the eigenvalues here tell me how much variance is in each row of the subspace, right? In each dimension. Makes sense. And the eigenvectors can be used to rotate that data. So they showed in the paper that the eigenvectors, the rotation by the eigenvectors, indeed gives you the linear independence that you need. Right? And then they said, hey, we have these eigenvalues. Let's figure out how to spread them apart such that each dimension has roughly equal variance. Right? So they said, okay, first we'll sort them. This guy's bigger, biggest eigen. He has the most variance. What I'm going to do is I'm going to make m buckets, because that's how many subdivisions I'm going to do. And I'm going to try to sort these in a way that every bucket has roughly the same variance, right? So I pick the bucket b hat, such that I'm going to pick the bucket with the smallest current variance, and then throw the next eigenvalue. So I say, okay, my first one, the biggest, I'll put this in b1, right? For my second eigenvalue, I don't want to go to b1 because it's already got some data in there. I'll go to b2, and the same for the next two. And then the next one's where it gets interesting, right? For the fifth eigenvalue, I'm going to pick the bucket with the smallest product of eigenvalues, meaning the smallest current amount of variance, and put it in there. That happens to be b4 in my two-dimensional example. And if you think about the fact that this guy's always bigger, it makes sense. So at the end of this, each bucket has roughly equal variance, almost equal variance. That gives them the guarantees they need. I take this result, and I encode it into a permutation matrix that I can then multiply the data by to spread that variance out exactly where I want. Make sense? Yeah, it's nice. I multiply that by Q, the eigenvectors, and that is my solution to R. Sweet, right? That's not that bad. The hardest part about that is understanding how I find these buckets, right? Which was
what did that give you, 5%?
What's that? Oh, you'll see.
No, but you're reprojecting it to a space where everything's even, and you don't have those those dots without anything in it.
Exactly. Yeah, we're actually just kind of rotating and spreading things out. It's pretty cool, right?
Yeah.
Yeah. Let's look at this is the wrap-up slide. This is our toy example, right? We're going to run this algorithm on the left, which is what we just discussed. We compute R. We can rotate the data by the inverse of R. Then we run product quantization, and then we get our results, right? Because R was originally defined as an operation on centroids, so we just rotate it. So if this is our toy example, I rotate it, move it to mean 0, all that fun stuff, and these are my resultant centroids, right? That's cool, great. Now I have, instead of a rectangle, I have, what's this called? Like shear. Yeah, parallelogram, right? A lot of work for parallelogram. But you can see there's not that guy out here in the corner, right? It's better aligned, yeah? It does minimize the distortion as much as you can given the centroids. Well, you gotta, oh, okay, cool. You're down? He's like, I buy it. I have sold it. So I measured the distortion on a toy data set I made for given a product quantization approach and an optimized product quantization approach. And the product quantization shown here in the dots, and the just average distortion shown on the left, and the x-axis here is the number of sub-centroids it is, k prime. Right? And I think I had m equal to 16 for all of it. So you can see it's lower, right? We have lower distortion, which means we're going to have higher accuracy when we do our search, right? Hopefully, yep. Yes, we do. It's up and to the left. Fantastic. I know. So this orange one is the optimized product quantization. This is, again, a recall at R curve. So this is the recall at 1 for our toy data set. And this is different number of neighbors.
Very nice.
So at recall at, I don't know, like 10, the toy data set's getting 100% for optimized. Regular product quantization takes it a little bit longer. So that's pretty sweet, right? Mm-hmm. Here's a result from the paper. This is also a recall at R curve. This is on a data set of 1 billion SIFT vectors. SIFT are a common vector used in computer vision. There are 128 dimensions of floating points. This is great. He's like, when you see this kind of difference, you publish it. Like epsilon, it's a big epsilon for an epsilon paper, right? It's cool, right? So optimal product quantization. Pretty simple idea, well executed. We're going to PCI align the data, use that eigenallocation to build a rotation matrix that makes everything independent and spreads out the variance. That gives us less distortion, which gives us better recall accuracy. No need to change our sublinear approach here, right? All I did was stick a matrix R into there, and everything worked out. Yeah, that's great. In fact, after you do all that work, when you're building your index, you can just multiply your centroids by R and then store them in the same way. So like the query part doesn't even need to know it was optimized, right? Pretty sweet, huh? So more accurate results. Now, somebody earlier realized, hey, there's something fishy going on here. Data's not normally distributed, right? It's for locally optimized product. Oh, we're finally at the paper. This is the paper I love. All right. So remember, multimodal data. If I did this for multimodal data, this is the optimized product quantization. You can tell because it's rotated. It's less grid-like. On this multimodal data of 5 nodes, right? I still have all these guys getting wasted. Yeah. Like the regular product quantization was pretty bad, but optimized is still not great. Right? But if you recall, we talked about that sublinearity. Remember, we had this sublinearity idea where like, hey, we're going to build this coarse quantizer and pack everything in, right? The guys who wrote LOPQ said, hey, if you're going to do this coarse quantization anyway, why don't you run optimized product quantization for each individual cell? Like, you're going to assign all these vectors to that centroid. So you already have them in groups. Just run it 5 times. So you build a separate quantizer for each sub-quantized value. Yeah, simple idea, right? Yeah, so they do this. Let's see what happens. So the key idea is create a coarse quantizer of big K cells, 5 in this case. Assign each reference vector to the closest centroid. Then run optimized product quantization independently for each group. Right? Cool, simple idea. When you do that, you get this nice spread that you have that we saw with the optimal product quantization, but there's no wasted space in the multimodal illustration. Sweet, right? Like, let's look at it side by side. So on the left, we have the LOPQ results, the locally optimized. And here we have slightly different parameters going on because there's this coarse quantizer. So my coarse quantizer is 5, meaning I have 5 groups. K prime is 3, meaning each of them gets 3 means per dimension. M is 2, so I'm cutting them in half. Right? That means I have 45 total centroids. Over here is optimized product quantization. There's no coarse quantizer. So it's just K prime is 7, M is 2. I have 49 centroids. But as you can tell, like, almost 10 of them are useless. Right? So they've solved that approach. So that's like a pretty simple idea. You guys were like, oh my god, another paper. And I'm like, wait, you already know everything. They just flipped that step, right? And what's not to love about this paper? So this is hilarious. In the original product quantization paper, they even said, hey, we could probably build a different product quantizer per Voyner cell, but it'd be memory intractable. LOPQ guys were like, no, not really. Here, I did it, right? And now, in their defense, though, the people who are at the product quantization paper, that was before the optimal part. So you didn't have as low of a distortion, right? So that was before that. So let's look at the results on our toy data set. Whoa. This is our recall at R curve. Recall at 1 using locally optimized product quantization. There's almost 30%. It's like 3 times higher. I compared it to optimal product quantization with the same number of centroids, because we have to do that thing with the coarse thing and all. And product quantization with the same number of centroids. And product quantization with the coarse quantizer, just to be fair. So this breaks apart each technique. So this one's product quantization with this coarse quantizer, same as locally optimal, but we're only building 1 quantizer. Whereas here we build 6 quantizers that are small. So we do much better, yeah? A big increase for not a big change in complexity, right? It's exciting. They were like, oh, wow. Let's look at the results from the paper. This is comparing LOPQ on the bottom on a billion scale data set, shown in blue. They use the multi-index technique. More than half the paper is describing how to use LOPQ on that multi-index, right? Where you use product quantization as the coarse quantizer. The idea was like, hey, use product quantization as the coarse quantizer, then use LOPQ kind of on each separately but in parallel, so you didn't blow things up. Right? So they did that for the billion scale data set. Shown in blue there, state-of-the-art results. Awesome. They compared it to optimal product quantization with the multi-index and product quantization with the multi-index, shown in blue. The green, the joint inverted index, is just the product quantization as the coarse quantizer, the paper we saw. And k-means LSH is the leading locally sensitive hashing technique that had the state-of-the-art before. So, fantastic, right? They're higher. It's the left. This was pretty exciting. So this is big scale, big data stuff, right? Okay, so just to wrap this up. We started off with quantization. We said, hey, quantization's cool. We can run k-means, get this nice packing, right? Nice distribution there. But it's like really expensive computationally. And even though it drastically reduced the storage costs, we need k to be way too big, right? So we said, let's do product quantization. We get so many more centroids for way less computation, right? But we have a lot of wasted space here. We're not getting as good distortion as we want. K-means actually got better distortions if you set k to the same value, right? But that was computationally infeasible. So we did optimal product quantization. We'll just rotate everything. We get a lower distortion, higher accuracy. That was cool. And then the LOPQ guys are like, hey, everything's multimodal, so just run that coarse quantization first, and you get a denser packet. Right? This is the figure from the paper. Now we all understand that figure. It took me like a long time. Cool, so I loved this paper because it was actually pretty self-contained the 5th time I read it. It explains relevant prior work, even though it's a conference paper. And then it builds upon it with actually a pretty simple idea, right? It solved it in an elegant way, too. Like, they didn't have to introduce that many new equations. They just showed you the equation for how to do it their way, which was like reversing supporters, right? And they did exhaustive experiments. So that's why I love this paper. No, it's okay. It's okay. Cool. So everyone can take their academics hats off now for a minute, and I'll talk about how some of the uses we have for this at Curalate, right? So I motivated this with a discussion of trying to find similar clothing, right? So we were building that, as you saw in the video, and we decided to use LOPQ as the technique of choice to apply that problem in the real world. We built it into a library in May 2017. We wrote it in C++. We used libeigen to get SIMD acceleration. Do you guys know what SIMD is? Some of you do. It's cool. It's like SSE or MMX. You guys remember MMX? MMX is SIMD, where you say, like, here's 4 values, add them to 4 other values, and you do it in one CPU cycle. So we get that for free with higher level libraries now. So we built it in C++, and we wrote Scala bindings around it because we write all of our stuff in Scala at Curalate, which sounds like merging, putting a horse in front of an airplane, which it is, which is why it's awesome, though, because how else are you going to get cutting-edge stuff to run really fast in modern service architectures unless you're combining these things? So we did that. That was pretty fun. So we did that last year, and we use it to power the product tagging stuff that we talked about. One of the interesting things about this that we did this for speed, not because we necessarily thought it was more accurate, was instead of building a coarse quantizer using k-means, we just used the output of the object detector as our coarse quantizer. So we assumed all the jackets were close together in space and all the hats were close together in space. So we got that one for free because the object detector said only look at hats. And that saved us a little bit of time. And we can certainly do it again within each one if we wanted to. But, we ship fast, right? Ship as fast, yeah.
So you say you got that for free, but it's built on previous work, right?
Oh, yeah. The object detector wasn't free.
Right. So
but by the time, we're at the bottom of that architecture.
He's using the classification that their customers made for him already.
Yeah.
Their customers are telling them that there's a hat.
Exactly.
And they assume that all the hats.
Oh, no. We use an object detector to tell us that's a hat.
Oh.
Yeah.
Yeah,
So,
so if you're using another algorithm already to detect the hat, would it be faster, or do you know offhand if it would be faster to do just from scratch the LOPQ?
It probably would be, it would definitely give us more accurate results. My answer. So yeah, it would be better to do that. We didn't do it in interest of time. It would be better to do that. But we actually, I don't know if I have this on the next slide. No, I don't. When we measured the approximation accuracy, and it was like 2% loss. Like our recall at 1 was 98% or something. So I was like, ship it. I'll take that. Instead of spending another day or two doing that part, we shipped it. So it was pretty cool. So good question. Yeah, it would definitely be better. You can always build more, right? At some point, you need to sell more. So it's pretty cool. So the space savings result were awesome. This is logarithm scale. This is showing the size of our indexes before and after we implemented LOPQ. So when we shipped version 0 of this, we actually used the KD tree technique and said, okay, we'll eat this M5 XL cost until we turn it on for more than 2 clients or whatever. So we shipped this, and we set M to 256 and K prime to 128, which means the number of centroids is really high, right? The number of possible centroids is super, super high. It means we could store 1 billion images in 8 terabytes, in 230 gigs of RAM instead of 8 terabytes, right? It's pretty sweet. That's a 97% reduction in storage costs, right? The executives were like, yeah. And I was like, raise? That's pretty cool. And then, I kind of pushed under the rug this neural net thing. But, we talked about projection matrices and rotation matrices. You can put a projection matrix in that neural net, take that thing down a few dimensions by running something like PCA, or there's deep learning techniques for that. We did that last fall, 6 months after we shipped the first version, which gave us a lower initial dimensionality budget. But we already had this LOPQ thing, so we're like, cool, let's run it again. And now, if that's 128, we set N to 32 instead of 256. We kept K the same. And now we can represent 10 million images in 256 megs of RAM. And that's our current data set size for the clients we've shipped the product for. Eventually, we could get 1 billion images in 26 gigs of RAM, but we haven't gotten there yet. So this is great. We fit all of our clients, there's the approximation error, is 2%. We fit all of our clients' images, all 10 million of them, in 256 megs of RAM. The thing runs on a Docker container with a max heap size of a gig. It's great. Right? It was awesome. So the run cost is nothing. The background cost is a lot. If you want to play with this stuff yourself, there's 3 libraries you can check out that are open source. Fast from Facebook Research, they released an implementation of this that runs on the GPU. It's the fastest implementation available. It wasn't open source. Their license is Creative Commons by, I forget what NC stands for. I don't know. It used to, what's that? What's that? No, it's not. It's like non-copy or something. I don't know. It wasn't open source when we had to build ours. And I emailed them. I was like, you guys going to open source this? Can we have it? Can we buy it? And they were like, no, we're not going to open source it for at least another year. And then they open sourced it 2 months after we shipped it. But if you want to play with this, they have the multi-index set up, the LOPQ thing set up, pretty good documentation. It's written in C++ and Python. It'll hit your GPU if you have one. Super, super fast. They can do that billion scale data set incredibly fast. The only problem I have with this library is it always crashes for me with a seg fault. So I don't. It's probably my NVIDIA driver. Yahoo has a library too. They used it at Flickr. It was written in Python. It's easy to read, and it supports Spark, which is cool. But it's not as fast as the Facebook one.
So when you say it's fast, like what's
time fast?
Yeah, give me a number, like hour, minute.
I didn't spend that much time on it. Yeah. The Facebook one, it's hitting a GPU to do that k-means.
Yeah,
it's fast.
Yeah.
But I mean, the stuff we wrote in C++ is web fast, so it returns in a few tens to maybe 100 milliseconds at the most. So that one I know the speed up pretty well, and that one we're not even hitting the GPU. So I actually think the Facebook one probably did a better job at making the code faster than we did. We just threw it at libeigen and said, SIMD is done, and that was it. Fast LOPQ is a library. It's a C++ port of the Yahoo one. So the Yahoo one's kind of easier to read. It supports Spark, but it's all interpreted. So if you want to play with this stuff, I recommend these libraries. We probably won't release our library because this one's better, and I don't want to write the documentation. I mean, I wrote it for my developers, but it's not very good. I might release the code I used to generate the figures if you guys are interested. That is very slow, but it's meant to understand the algorithms. So it implements the algorithm, but it's all in Python. And it's pretty slow. There's been more recent work in this. There's a few papers that I haven't gotten into yet. This one was at NIPS last year, and they, I think, beat the LOPQ accuracy. This next one, it says it's under review, and I found it on GitHub, so maybe it's like a preprint. Maybe it'll never get reviewed. It seemed interesting.
I'm guessing that second one was what I was thinking. Was that you don't need to have why have the same number of grid points in each one of the blobs? I mean, if you have a big blob, have more points there, fewer points.
Yeah, so you could totally use a data-driven technique for the number of points.
Maybe that's what asymmetric mapping is doing.
That would give you a better compression for sure, but it'd be at the cost of having to store before you. You'd have to store somewhere hey, this one has 128. This one has.
Right, it makes all
it's just, but it's just a little bit more. It's not it's not going to add extra storage space. It's just going to make a little bit more. But yeah, totally could. At Curalate, we're interested in putting this into Elasticsearch. So each of those individual things could be represented by a hex code. Throw it in Elasticsearch. It handles that coarse quantization for you. Then you re-rank by your distance function. It'd be pretty cool. It would allow us to scale out a little bit at the cost of actually spending more storage, ironically, because the string takes more to store than a bit. We also kind of want to see what else we can do with other approximate nearest neighbor applications and use our product search in other fun ways. So I'm going to give you a preview of something that's coming that you'll probably never see because we're going to release it. And whenever we release something to the public, nobody uses it. We build stuff. We're B2B. So whenever we try to go B2C, it doesn't work. So I'll give you a preview here. So this is an Instagram page. And we built this bot that if you go to the page and say, hey, add bot to shop, it'll reply with a link to a website where we ran the visual search and recommended the products to you. So you can, if you're on Instagram, you can just shop it automatically. We're going to try to get this to go viral, which didn't work last time we tried to get something to go viral. But we're going to try to get it to go viral soon. So, yes. I'm sure many of you remember the last time we tried to go viral. It was deep learning stuff at school. All right, so thank you very much for your time. I'll answer any more questions about the paper that I can. Now, does anyone have any thoughts? Yeah.
Do you get any benefit in accuracy if in that first pass of bidding you scale the number of centroids to the number of input nodes that are in each of those groups, so that you allocate more centroids to the groups with more input nodes?
Yeah. So more centroids is always more accurate.
Right.
In all of the techniques.
But I mean, does anybody do that in practice? It's like
I'm not sure. I'm sure, probably.
It's like, what do you call it, DVR encoding.
Yeah, right. I think that's similar to what Walt was saying. It's like, hey, like, you make these things dynamic, you get better accuracy.
Yeah, just allocate more bits where.
Sure. I don't know of anyone doing it, but this is the first time I've talked about this publicly, so I was hoping some of you guys had done it.
Maybe sit next to you.
Yeah.
Before this.
Thanks. Any other questions? Cool. Thanks for your time. And Ted is trying to get someone to run talk. Oh. Okay.
For that, let's give you a hand.
Oh, thanks.